Hello everyone, welcome to my YouTube channel. Today I am going to talk about epimers and anomers, and I'll try to explain you in a very simple manner the concept of epimers and anomers. Epimers and anomers are stereoisomers that differ in configuration at one chiral center only. Although they contains more than one chiral carbon, which is mandatory that they must contain two or more chiral centers, but they have different configuration at one chiral center only, or you can say at one stereogenic center only. If the concentration is different at the anomeric carbon, the configuration is different at anomeric carbon. Now, what is anomeric carbon? Anomeric carbon is the carbon which contains an aldehydic or a ketonic group, like it may contain a CHO group or it may contain a ketonic group. And when the molecule, in order to stabilize itself, form a ring structure, like when glucose forms a glucopyranose ring, then this anomeric carbon involves its oxygen in forming the cyclic structure, and it acquires a OH group during the formation of glucopyranose ring structure. So if the configuration is different at anomeric carbon, then they are called as anomers. But if the configuration is different at any other chiral center except the anomeric carbon, then they are called as epimers. This is the basic difference. And with the help of example, it will be easier for you to understand the concept. So first, see this example. Here two molecules are shown on the slide. Both these molecules contain 5 carbon atoms, and out of these 5 carbon atoms we have 3 chiral centers. The C2, C3 and C4 molecule in the C2, C3 and C4 carbon atoms are chiral in both these molecules. If you notice that at carbon number 2 and 3 we have, on one side we have OH on left, at C2 as well as C3 also we have OH on left, and in the second molecule also we have OH on the left at both C2 and C3, which means that the configuration is same at C2 as well as C3 carbon atom. But if we look at the carbon number 4, which is given in blue color, so at carbon number 4 in the first molecule, OH is on the right hand side, while in the second molecule OH is on the left hand side, which shows that they have a different configuration at C4 carbon atom, and therefore these two molecules are said to be epimers of each other. And since the configuration is different at the fourth carbon atom, so we write here C4 epimers, because it is a practice, usual practice, that while writing the name of epimers, we always mention the carbon atom at which the configuration is reversed, the configuration is different. So it clearly gives an idea to the reader that at which particular carbon the two molecules are different, are having different configurations. Similarly, we have an example of anomers, actually two examples of anomers. Uh, so if you see this molecule, the first two, these are two molecules of glucopyranose ring. One form is alpha form and the other form is beta form. This one is called as alpha D glucopyranose, while the bottom molecule is called as beta D glucopyranose ring. So as we all know that the glucose under normal condition, it is having a structure where it has 4 CHOH attached to it, and the first molecule contains an aldehyde group, while the last molecule, the C6, the 6 carbon, contains an alcoholic group. Now when it forms a glucopyranose ring, then this oxygen, because this is the anomeric oxygen, this oxygen combines with this carbon atom to form the ring structure. Both these structures, we have a hexagonal ring in which 5 carbon atoms are part of the ring and the 6th is oxygen atom, 4, 5, and this is the 6th carbon atom, while oxygen takes the one vertex of the hexagonal ring. Same is the case here. This is first, this is second, then we have third, 4, 5, and this is 6, and this oxygen takes the hexagon 6 vertex of the hexagonal ring. Now when in this structure OH is at the bottom going shown at the bottom. So it is called as alpha D glucopyranose ring, and this one where OH is pointing upward, this is called as beta D glucopyranose ring. These two, alpha D glucose and beta D glucose, are anomers of each other, and they are very more common example of anomers. Similarly, we have which are formed from fructose. Whenever we have OH group pointing downward, it is alpha form, while if OH is pointing upward, this is called as beta form. So these are the two examples of anomers. In the other slides, I'll discuss more about epimers and anomers. And now I will tell you some important features of these epimers and anomers. They are, first of all, epimers and anomers are possible only if the molecule contains more than one stereocenter. If the two molecules have only one stereocenters, then they are neither anomers nor epimers. This is the first thing. And if they have more than one chiral carbon atoms, then the configuration should be different only at one carbon atom. For example, they have 3 or 4 carbon atoms which are chiral, but out of those 4 or 3 chiral carbons, they have different configuration at 2 chiral carbons. Then in that case also they are not epimers, neither epimers nor anomers. The condition criteria is that they must have more than one chiral centers, and out of those chiral centers they have different configuration at one chiral center only. And if that chiral center where the configuration is different is anomeric carbon, they are called as anomers, and if it is not anomeric carbon, they are called as epimers. And the third condition is that since they have different configuration at one carbon only, they are not enantiomers, they are distereomers. Let us move to the next slide. Epimers again, as I said, they are distereomers because they contains more than one chiral carbon atom, and out of those chiral carbon atoms, they have different configuration on one carbon atom only. Epimers are not the mirror images, as you see that in this particular molecule, the carbon atom number 2, which is a chiral carbon, is shown in blue color because it has a different configuration at this particular carbon atom here, while at other carbon atoms, chiral carbon atoms C3, C4, C5, the configuration is same. But in this blue colored C2 carbon, in case of D-glucose, H is on the left, OH is on the right, while in case of D-mannose, OH is on the left, H is on the right. Since the configuration is different, so we can say that it is a epimer because it is satisfying, it is following all the rule. The first rule says that epimer, which shows that glucose, D-glucose and D-mannose have different configuration at C2 carbon atom only. So this C2 carbon atom is called as the epimeric carbon. In these two molecules, the configuration is different at all these 4 chiral carbon atoms, and therefore there are enantiomers. But since they have different configuration at more than one carbon atom, they are not epimers because they are not following the condition for epimer. Let us see the other example. In this example, there is one chiral center only, and as I said, for molecules to show epimers or anomeric property, they must have more than one chiral carbon atom, and since in not epimers, they are also not epimers. Let us move to anomers. As I said before, anomers are those stereoisomers which have different configuration at their anomeric carbon atom only, and which is generally C1 in case of glucose, galactose, but in some cases, for example in fructose or in other, generally it is C1, but it may also be C2 or neither, but it must contains an different configuration. It's anomeric carbon, and anomeric carbon is the carbon which contains an aldehydic or a ketonic group, and when they form a pyranose ring, when they form a ring structure, in order to improve their stability, that carbon contains an OH group, and that carbon also involves in the formation of ring through its carbonyl oxygen. जो उसका ये वाला कार्बोनिल ऑक्सीजन होता है, उसके थ्रू वो रिंग बनाने में हेल्प करता है ऐसे करके यहाँ से रिंग बन जाता है और इसकी दूसरी साइड में OH रहता है। इसको एनोमेरिक कार्बन बोलते हैं। For example, you can here see that this is alpha D glucose and we have an example of beta D glucose. They are basically in the form of pyranose ring. So here this these structures basically exist in this particular form. So this beta D glucose exists in this form and alpha D glucose exists in this form, and it is very easy for you to understand the concept that look at this one C1, and C1 is directly connected to oxygen. Here also C1, we have alpha D glucose C1, C1 directly connected to oxygen, and then on the other side C1 is connected to C2, C3, C4. Here also C1 is connected to C2, then we have C3, C4, and the last part of this ring is C5. We have again C5. So this is a hexagonal ring in which there are 5 carbon atoms and 1 oxygen atom to form this hexagonal ring. This sixth carbon atom is not the part of ring. It is connected to carbon atom number 5 and it is outside the ring. In case of alpha D glucose, similarly in case of beta D glucose also, this sixth carbon atom is connected to fifth carbon atom, but it is not the part of ring. The ring is formed between C1, C2, C3, C4, C5, 5 carbon atom, and again 1. The sixth is oxygen atom. So in this structure also, since OH is downward in alpha D glucose and OH is upward in beta D glucose, so they are anomers. Let's discuss few more examples of anomers, alpha D glucopyranose and beta D glucopyranose. And in these two molecules of alpha D and beta D glucopyranose rings, we can see that because in case of glucopyranose we have the C1 carbon as the anomeric carbon here also, and at this C1 anomeric carbon we have OH going downward. Here we have OH pointing upward. So this is the alpha D glucopyranose and this is the beta D glucopyranose, for your better understanding. And then in the next example of alpha D fructofuranose and beta D fructofuranose, they are also anomers because again at the anomeric carbon, since in case of fructose it is the carbon atom number 2 which is the anomeric carbon. So in these two examples you can see that this at this anomeric carbon OH is going down, so again this is alpha D fructofuranose, and here OH is going up, so it is a beta D fructofuranose. Let me show you one more example of methyl alpha D glucopyranoside and methyl beta D glucopyranoside. Since it is methyl glucopyranoside, so the OH of anomeric carbon is replaced with OCH3. So it doesn't matter whether it is OH or OCH3, but if OH or OCH3 is downward, it is called as alpha form, and if it is OH or OCH3 is going upward, it is showing the beta form. So as in this case, we have OCH3 down, so this is the methyl alpha D glucopyranoside, while here we have OCH3 up, so this is the methyl beta D glucopyranoside. This is another example, and I hope it is now the concept of anomer is now clear to you. Some similarities or interesting features of anomers and epimers: they are stereoisomers, and both these stereoisomers, they contains more than one chiral centers, more than one stereo centers, and out of those stereo center they have different configuration at one stereo center only. And these anomers and epimers are commonly found in case of sugar molecules like glucose, galactose, mannose, fructose. They all are sugar molecules. These sugar molecules commonly shows anomeric or epimeric isomerism, and since they show isomerism because of the position of OH, sometimes it is on the left side, sometimes it is on the right side, or maybe up and down. Therefore they show isomerism because of this OH group position only, which may be either epimer or anomer. And as I said before, they are not enantiomers because the configuration is different only on one carbon, not at other chiral carbons. Therefore they are not enantiomers, but they exist as diastereomers. So this is all about anomers and epimers, and I hope that with this video you have a better understanding, and